Hey there, everybody. Welcome to another online lesson. This is the first online lesson in terms of the real meat and potatoes for organic chemistry. So if you haven't checked out the introduction that sort of just introduces us to carbon and why carbon is so important, I encourage you guys to check that out. But this is going to be the first very, very essential lesson for Organic Chemistry 1. So let's get started with hybridization of carbon. This is part of my Chem Complete series, so my goal is to have all of these Organic 1 videos put up over fall of 2015. But let's go ahead and get started with this. So the first thing we're going to talk about in the first couple lessons is hybridization. What is hybridization? And particularly since we're doing organic chemistry, we're interested in hybridization with carbon. So a hybrid orbital is something that comes from the merging of two orbitals. So when we're considering carbon in organic chemistry, carbon only has access to s and p orbitals. So that would be an example. And we would take those, the s orbital, the 2s orbital, and the 2p orbitals, and we could merge them together to create new hybrid orbitals, which we'll take a look at in a minute. But one of the questions we kind of want to address is why does hybridization actually occur? And when I say the term occur, hybridization is a bonding theory. So it's almost like if you're familiar with resonance, when you say resonance structures occurring, there is no real resonance structure. It's a theory about how electrons are moving around in all the possible positions. So hybridization is a theory, but we're going to use the term occurs. So why does hybridization occur? There's two main reasons that drive or explain hybridization. The first one is that it lowers the energy requirements during bonding. And the second one, another important piece, is that it's going to improve the overlap. So when I bring, this comes from, valence bond theory. When I bring two elements or atoms together and I want to create a bond between them, the orbitals that contain the electrons, remember that a bond is nothing more than two electrons. So the orbitals that contain those electrons need to have decent overlap when we come together, especially in covalent bonds when we're talking about sharing these electrons. I need to have overlap between the orbitals. So what we're going to take a look at is orbitals that are available. So what kind of hybrids could I make? Again, a hybrid is a mixing of two orbitals. So here's a couple examples. Hydrogen only has s orbitals. So if I think of the structure of hydrogen, hydrogen only has a 1s orbital. And so hydrogen cannot create any type of hybrid orbitals because it only has s. You would need a p or something else in order, sorry, that just popped up there. You would need a p orbital or some other type of orbital to mix with the s orbital in order to form a hybrid. So then we take a look at carbon. Carbon is in group 2, and we have s and p orbitals, so we can form sp hybrids. And this is where, if you've heard in general chemistry, sp, sp2, and sp3, we're going to be talking about each of those in these video lectures. This one will cover sp3. There will be a separate one on sp and sp2. And then finally, if you take a look at sulfur, sulfur, while it does not currently, if you take a look at the Lewis structure, it would not currently hold electrons in its d orbitals. They're left empty. Anything that is in row 3 or below on the periodic table technically has access to d orbitals. The first set of d orbitals are 3d. And so a sulfur has sp and d orbitals, so sulfur can create sp orbitals, and it can create spd hybrids. So that's kind of important to keep in mind, that you can have more than just two orbitals coming together when we're merging and creating these hybrids. You can have spd orbitals when you're creating the hybrids. You could throw in f's if you got far enough up on the periodic table. I guess I should say far enough down, right? We are not going to be focusing on or very interested in spd hybrids. And the main reason for that is, as we talked about in the introductory lesson, carbon, hydrogen, oxygen, nitrogen, and some of the halogens, so yeah, chlorine and bromine could have access to some of those d orbitals, but the bulk of the elements we're dealing with in organic chemistry are limited to the second row or above, specifically if we're talking about hydrogen. And so we cannot go past octets in that case. We cannot expand our octet because we don't have d orbitals available, right? If carbon's in row 2, it doesn't have access to a 3d orbital in terms of its valence shell. I do not know why this keeps popping up here. Give me a second. Change the color, keep the current scheme, keep the current color. Don't show this message again. Sorry about that, guys. Don't show the message. Okay, so let's continue. Oh, by the way, at the bottom here, I have represented the s and the p orbital. So keep in mind, the s is just a regular spherical orbital, very close to the nucleus. The p's extend a little further from the nucleus, and we have three different types of p orbitals: px, py, and pz. So when we create hybrid orbitals, what we're really doing is we're merging the two orbitals. So this is a very simple diagram, but I'm taking an s orbital and a p orbital. I merge them together, and I get an sp orbital in return. And you can see that this still has somewhat of the dumbbell shape, but it's very lopsided, right? The top side that we see there is very large in comparison to the bottom side, and that is a sp orbital when I have mixed the two potential orbitals together to create the new hybrid. And that larger portion is the portion where we're going to find the electron density, and the electrons in those large portions will have nice overlap with one another when we're creating things like carbon chains or something like that. Okay, so when we want to talk about hybridization, and we're going to go to sp3 first, then we'll do sp2 and sp in a separate lesson, we want to consider the orbital diagram for carbon when we're doing this hybridization. So if you recall your orbital diagrams from general chemistry, carbon has a 1s that is completely filled with 2 electrons, a 2s, and a 2p. Now you should be familiar with the way that we fill these orbital diagrams, all right? So starting at 1s and continuing upwards, we're climbing in our energy. And that's because 1s is closer to the nucleus than 2s is closer than 2p, etc., so on and so forth. The closer electrons are to the nucleus, the closer in proximity they are to the protons, and so that's a stabilizing factor. If you go back, you look at effective nuclear charge, some of those other general chemistry concepts. Okay, so when we take a look at the carbon orbital diagram, 1s is filled with 2 electrons, and then I get to the valence shell. And the valence shell is basically the outer shell that has electrons in it. And carbon has 4, so if I go across the periodic table, I would have lithium and then beryllium, that's 2. Boron would be 3, and then I hit carbon, which is 4. And so carbon has 4 electrons available to it in its valence shell for bonding. And we have 2 of them paired in the 2s and 2 of them unpaired up in the p orbital when we're looking at this. So we have to keep in mind, hybridization, the theory of hybridization, basically says hybridization is going to explain bonding. So if we're just dealing with an isolated carbon atom, we're not too concerned about hybridization. We're really talking about when bonding is involved. And so I've highlighted in red here the valence electrons, right? So it's only group 2. Group 1, those electrons are not available for bonding based on valence bond theory. And so what we can do, the way I want you guys to think about this, is that when I create hybrids, imagine that I'm taking any orbitals of interest that I want to create hybrids out of, and I'm either putting them in a blender or I'm mushing them up, and I'm creating these brand new hybrids, and they sort of come off of a factory line, right? So what I'm going to do, if I want to do an sp3, the 3 is referring to how many p orbitals are going to be recruited, or how many p orbitals are contributing to the hybridization process. So anything that's sp3, it means 1s and 3 p's were recruited. Now this is important to realize because a lot of students think it's the number of electrons that are found, and that is not correct. When you say sp3, we're not saying that there's only 3 electrons found in those hybrid orbitals. There's actually going to be 4. The sp3, the s comes from the fact there's 1s. The p3 comes from the fact that I have 3 p orbitals, and I am recruiting every single one of them in the hybrid process. All right, I just want to clarify that. So what we do, we mash these up, right, and we create 4 new orbitals. And if you take a look where I'm placing this, okay, the energy of these hybrid orbitals is going to be slightly above the s, but it's going to be below the p. And so we said one of the benefits of this hybridization is that we're talking about lowering the energy requirements for the bonding of the electrons. Okay? And so I get 4 orbitals out. Now think about that. I put in an s and 3 p's. That means that if I put 4 in, I can get 4 out. And so I have 4 hybridized orbitals. These are called sp orbitals. That doesn't mean this is sp hybridized, but we're referring to each one of these orbitals, right, that we see right here, right here, right here, and right here. All right, those 4 are your hybrid orbitals, your sp orbitals. Now, once I have created these, so to speak, again, we're talking about this in theory, but once I have my hybrid orbitals, those are the new orbitals. The s and the p orbitals, in theory, are gone. I've created these new hybrid orbitals, okay? And once I have them, I need to do something with my electrons. I had 4 electrons over here. I'm not going to leave them homeless, so to speak. I need to find a new home for them. Well, if they originally were found in the s and the p, they're going to come over to these sp orbitals. And you still want to follow the same electronic rules that you learned in general chemistry. So Hund's rule tells us that what was originally in the valence shell is going to come over to these hybrid orbitals that are now in the valence shell, and I'm going to fill them one at a time, right? So just like this, if I go back and you take a look, I had 4 electrons here. I take all 4 of them and I put them here one at a time. And if you draw the Lewis dot structure for carbon, that's exactly where those 4 dots are coming from. I've got 4 of these individual electrons that are going to participate in some sort of a bond. Keep in mind that Lewis structures, the whole point of drawing Lewis dot structures is to show bonding, okay? And so the 4 electrons, when I draw them around carbon, I'm talking about these 4 hybridized electrons that can be involved in bonding, okay? And so I would refer to this, notice also I just want to point out the 1s, that's still down there, right? These are not valence electrons. They don't get pulled up here. They're not available for bonding. Only valence electrons can be emptied out into new hybrid orbitals for bonding. Okay? And so this is referred to as sp3 when I have this configuration. Again, sp3, 1s, 3p orbitals. I have the 2s. There's only one 2s orbital, but there are 3 2p orbitals. 2px, 2py, and 2pz. I recruited all of them and brought them over here, okay? So even though I have this up here for the purpose of representing the way this occurs, don't think of these 2s and these 2p's as available anymore. I've created the hybrids, okay? Now, we've got 1s orbital and 3p's that were used in this process, and so I refer to this as sp3. All right. So, when we have sp3 hybrids, any carbon that has 4 individual single bonds, and these are referred to as sigma bonds. So you've probably heard a lot of teachers talking about sigma bonds and pi bonds. Any single bond is going to be called a sigma bond. If you have 4 single bonds around a carbon, and that's the most that you can have, don't ever draw a carbon with 5 bonds, okay? That means you have an sp3 hybridized carbon. So anytime I find a carbon with 4 bonds, it's going to have an sp3 hybridization when I'm looking at classifying its hybridization. Okay? Every sigma bond, so every single bond, is going to be the result of a hybrid orbital. It's going to occur in a hybrid orbital. We'd call it a hybridized bond. Anytime you have pi electrons, and we will talk about that more in the next lesson, pi electrons or pi bonds, those are going to occur in p orbitals, not in hybrid orbitals. So, to give you an example, here's methane, right? I have carbon at the center. I have 4 single bonds to these hydrogens. The carbon is sp3 because I have 4 sigma bonds. Every sigma bond is going to be considered a hybridized orbital that's, taking place in terms of this bonding. Notice that all the hydrogens are H. All the hydrogens are S, right? So we talked about that at the beginning of this lesson. We said all hydrogens must be S because they don't have P, right? We don't have that availability. And so if you take a look down here, the carbon, right, which would be at the center here, has these 4 hybrid orbitals, sp orbitals, and it's sp3 when we consider its total hybridization. The hydrogens are just S. And so if I attach them to each one of these positions, this would be the orbital diagram representation, not molecular orbital. We're not talking about MO theory here. But this would be the hybridized orbitals and the orbital overlap that you would see. Okay, so a summary of what we talked about here so far. Number 1, hybridization lowers energy requirements when we're involved with some sort of bonding, and it helps to improve orbital overlap. So when we have two electrons in separate orbitals have to come together in order to form a bond, we get improved overlap with hybridization. Number 2, hybrid orbitals are a merging of 2 or more orbital types. For carbon, and we're really going to just focus on carbon in organic chemistry, for carbon, we're talking about s and p orbitals. Again, hydrogen could not create hybrid orbitals because it only had s. I need 2 or more. That's the definition of a hybrid. And then finally, number 3, sp3 carbons contain 4 sigma bonds. Again, those are single bonds. And they use all s and p orbitals in creating hybrids. So again, anytime you see a carbon, like methane or any other thing, carbon tetrachloride, something like that, if I have 4 single bonds or sigma bonds around that carbon, it is sp3 hybridized. Okay, so for the next lesson, a little preview. We're going to be talking about sp2 and sp hybridized carbons. A little bit more complex, but not a whole lot. We have to consider pi electrons and p orbitals. It turns out that pi electrons will only be hosted in p orbitals, not hybrid orbitals. And we will sort of, going along with pi electrons, be talking about double and triple bonds. But that wraps up the lesson for right now. So thank you very much for taking the time to learn with me online. Please remember to like the video if it was helpful. You are free to comment if you would like to leave comments, if you found it helpful, if you have questions. And then please also subscribe. That would be a huge favor for me. There's a blog link in the description. I am currently updating and working on a site, so you can get links to the site. It'll be a blog/site with information. And this has been a Chem Complete presentation. So I will see you guys for the next lesson. Thanks a lot.